Hi, this is Beth Secord, and today we're going to be talking about understanding inductive and statistical arguments. So this lecture is two lectures put together. They work well together, but it is long and we'll be covering a lot of different points. So let's review from last time. So the anecdotal fallacy, or the problem with reasoning by anecdote. So anecdotal evidence, stories from your friends, single cases that you can remember, intuitive guesses, recollections from your own experience are usually not good enough grounds for drawing conclusions about trends, rates, or large-scale phenomena. So the fact that your friend had something happen to her when she went to the hospital, you can believe your friend that happened, but you can't make any assumptions about the way that all hospitals are from your friend's experience. So the anecdotal fallacy is when people make sweeping generalizations on the basis of one case. So your anecdotal fallacy journal, which is due Friday, you'll have to think of a time when a friend or you yourself or someone you know used the anecdotal fallacy to make some sweeping generalization based on just one case or one story. So a scientific approach, on the other hand, requires statistical reasoning as well as causal reasoning. We'll talk about causation next time, but today we'll talk about integrating statistical reasoning with inductive reasoning. So let's compare the scientific statistical approach with the anecdotal approach. So suppose that you're at Thanksgiving dinner and the topic of nuclear power comes up, and someone says nuclear power is too dangerous. My uncle died in an accident at Wolf Creek, and then the person says people die every year in accidents at nuclear power plants, and that's the fact that the person knows someone that died in a nuclear power accident makes it seem as if nuclear power is a very dangerous type of work. Perhaps it is dangerous to the public, but let's just look at this one argument for workers. So the scientific approach looks at the actual statistics. So look at the actual statistics here. Last year, I think this is data from 2015, 3 out of the 120,000 nuclear power workers died. Oh, in 2010, so that's 0.0025% of the workers. Compare that to coal miners, where 48 out of 82,000 died. That's almost twice as dangerous. Coal mining work is almost twice as dangerous as nuclear power work. So the fact that your friend's uncle died in an accident makes it seem as if nuclear power is the most dangerous type of energy work. But if you look at the data, if you compare that to coal mining is twice as dangerous. Another problem with the anecdotal fallacy is that your own sampling will not be representative because you are situated in a certain context. So suppose that you are an emergency room nurse, or suppose you ask an emergency room nurse about the dangers of recreational drugs, and the nurse will tell you all sorts of horror stories because her sample comes from all the people she sees in the emergency room who have OD'd on drugs. So she has a skewed sample. The only people she ever sees are going to be people who have abused drugs and are having horrible effects. Her sample is the people in the emergency room. So your personal encounters with cold remedies, beauty treatments, power plant workers, or drug addicts is not necessarily representative of everybody, not representative at all. So, so here's just further. Your intuitions, personal history, or stories aren't going to be reliable indicators of any sort of trends, facts, or large-scale phenomena. So perhaps you went to San Francisco and you got mugged. It would make you feel as if San Francisco is a really dangerous place. And here's the anecdote. San Francisco is way more dangerous than Sacramento. My husband got assaulted while he was walking down the street. But then you can compare the assault rates for the two cities. San Francisco, 2.5 per thousand, versus the assault rate in Sacramento, 4.5 per thousand. So Sacramento is twice as dangerous, about twice as dangerous as San Francisco. So statistics are used in inductive arguments as part of inductive arguments, but what are inductive arguments? So we'll take a step back and look a little bit at inductive arguments. So inductive arguments, let's contrast them with deductive arguments. So deductively valid arguments, if the premises were true, would guarantee the truth of the conclusion. So we already studied deductive arguments. Deductive arguments, the truth of the premises guarantee the truth of the conclusions. But inductive arguments aren't like that. Inductive arguments, the truth of the premises does not guarantee the truth of the conclusion. It only makes the conclusion likely. So in an inductively valid argument, the premises, if they were true, would make the conclusion likely to be true. And we're defining likely to be true as greater than 50% likely. So in an inductive argument, if the premises are true, if they're believable, they make the conclusion likely or probable, but do not guarantee it. And that is the main difference between, the only difference between deductive arguments and inductive arguments. So deductive arguments guarantee their conclusion. Deductively valid arguments, inductive arguments do not. They only make their conclusion probable. So because inductive arguments only make their conclusion probable, they will not be deductively valid. So we'll be using the terminology inductively valid because it's symmetrical. If the form is a good one, it's an inductively valid argument. Other textbooks use other terms like strong. We'll talk about arguments being inductively valid and reasonable. So here's some terminology. So inductively valid refers to the form of the argument. So some textbooks in logic will call this a strong argument, just so you know. But we're going to call it inductively valid because I think that's easier to remember. It means it's like valid for a deductive argument, but it's valid in the inductive case. And then reasonable refers to the whole argument, both the truth of the premises, the structure of the argument, and the truth of the premises and the conclusion. So some textbooks call this cogent if the whole argument is inductively valid and the premises are true, then textbooks call this cogent. But we're just going to say that it's reasonable to believe. So if the form is good, if it's inductively valid, if it has believable, true premises, then we'll call the whole argument reasonable to believe. So just drawing a connection between what we studied last time. So validity, inductive validity is like what we talked about last time. Validity and reasonableness is parallel to soundness in the deductive case. Okay, so here's an ordinary example of inductive validity. So here's our premises. Smith's fingerprints were on the murder weapon. A security camera shows Smith committing the murder. The murder weapon was found in Smith's home. Therefore, Smith is guilty of murder. So this is an inductive argument because the truth of the premises, let's suppose those are all true. They are Smith's fingerprints. There was a security camera that showed Smith committing the murder, and the murder weapon was found in Smith's home. Those are all true. It doesn't guarantee the truth of the conclusion. It only makes it probable. So it's very likely, given all these three premises, that Smith is guilty of murder, but it's not ironclad like a deductive argument. So why isn't it ironclad? So the premises could be true and the conclusion false. So how could these all be true and this false? Well, it could be that Smith's fingerprints were on the weapon, but they were they were placed there. It was planted. It could be that the murder weapon was planted in Smith's home. It could be that Smith's doppelganger, someone dressed up as Smith, is shown on the security camera. So he could have been framed. There could have been a mistake. Witnesses make mistakes. But in general, the conclusion is probably true, most likely true. So that's the main difference between inductive and deductive arguments. We talked a little bit about what does it mean to say that something's probably true or likely to be true. Now there's disagreement about how likely the conclusion of an inductive argument has to be in order for the whole argument to be a good one or a reasonable one. At least it should be over 50%. So when the probability and the conclusion exceed 50%, the scales tip toward its being true. So some philosophers say, 60, 75%, 85% I've heard, but at least greater than 50%. So we'll just go with that. When the probability of the conclusion exceeds 50%, then we can say that the argument is more or less reasonable to believe. So here's an example of inductive validity, an argument that's inductively valid. So let's say that 85% of UNLV students are beer drinkers. And let's say that Sarah is a UNLV student. The conclusion here of this inductive argument is that Sarah is a beer drinker. Now, there's an 85% chance that Sarah is a beer drinker. She's probably a beer drinker. This argument is inductively valid. It's also reasonable. This is true. Let's just pretend this is a true statistic. True. We'll say this is true. Then the conclusion is not guaranteed. It could be that Sarah is part of the 15% that doesn't drink beer, but Sarah probably is a beer drinker if she's also a UNLV student. So this would be called an inductively valid and reasonable argument. But you can see again that the conclusion is not ironclad. Okay, here's another one. The odds of being killed by a vending machine is 1 in 112 million. So there's and let's translate that into a percentage. So there's a 99.9999% chance of people. Oh, this is typo here. Just fix that. Oh, won't let me fix it. Okay, we'll pretend that this says there is a 99.999% chance that you will not be killed by a vending machine. You are a person, therefore you will not be killed by a vending machine. So this is a very reasonable, it's very strong. This is inductively valid, and it's also reasonable to believe that you will not be killed by a vending machine in your lifetime. But it's not guaranteed. So there's a 0.00001% chance that you may be killed by a vending machine. So be careful. Be careful out there. Now, this is an interesting point. A lot of people think, and this comes up in debate about scientific theories, that if scientists are not, and it's probably one of the main reasons, not the main reason, but a large reason why global warming denial still persists, is that people think that you need to have 100% certainty in order to know something. So, do you know that you won't be killed by a vending machine? Well, yeah, you can be pretty sure you're not going to be killed by a vending machine in your life. You can be pretty certain about it. You don't have 100% certainty, but you do know. Okay, so some people insist that if we don't have absolute certainty, then we don't know anything. But this is a mistake. If absolute certainty is necessary, then there would be too few things that you actually know. So in philosophy, we point out that the only thing that you can be 100% sure about is that you exist. Everything else would be up for grabs. But it seems like that's too strict of a definition of knowledge. You know a lot of things. You know you're sitting in a chair right now, you have a computer screen in front of you or not. You know that you're inside, you know that you have hands, you know that today is, this month is March. You know all of these things, even though you're not 100% sure. For all you know, you could be inside a computer simulation. You just think that you have hands, but you don't really. So here's some things that we can say that we know, even though we're not 100% sure about them. So you know that the sun will rise tomorrow, even though it's not 100% guaranteed that the sun will rise tomorrow. You know that smoking causes cancer, even though we're not 100% sure that smoking causes cancer. There's a 0.0001% chance that some other factor is causing cancer. You know that the American Revolution happened in and around 1776, even though there's some chance that the history books are all propaganda. We still know that, even though it's not 100% certain. You know that the bubonic plague is caused by the bacteria Yersinia pestis, even though it's possible that scientists are mistaken. It's not very likely. So we do know things if they are highly likely, highly probable. If you said that you didn't know things that weren't 100% certain, you would know nothing. You would know next to nothing. So we know all these things. You can say that you know them. You say that you can be pretty sure about them, even though we're not 100% certain. There's a 0.0001% chance that we're mistaken. And this ties back to what we talked about, fallibility. You can be justified in, you can have a justified belief that's very justified. It turns out to be false, even though you've done your due diligence. So there's still a small chance, 0.001% chance, the sun will not rise tomorrow. The bubonic plague was caused by something else. A valid inductive form. Okay, so let's talk about induction. Okay, so this is the form that's being used. Here it is. So most A's or B's, so most can be, you could insert a statistic there, 90% of A's or B's, 85% of A's or B's, 85% of UNLV students are beer drinkers. You say typically, usually the majority. Sarah is a UNLV student, X is an A, so X is a B. So this is a valid inductive form. It's very much like modus ponens, which we looked at last unit, where all A's are B's, X is an A, so X is a B. This is a deductively valid form. The conclusion is guaranteed. And here this is inductive. It says the majority instead of all, so the conclusion is not guaranteed, but it's made likely. So this is a valid inductive form, valid deductive form. They have a similar format, a modus ponens-like format. So here's an example. Most A's or B's, most of the substances that are carcinogenic for mice are carcinogenic for humans. Most A's or B's. X, benzene, is A. Benzene is carcinogenic for mice. Therefore, X is B. Benzene is carcinogenic for humans. So you can see how this follows the modus ponens-like structure. Most A's are B's, X is an A, therefore X is a B. It's inductively valid. Here this conclusion says that it's most likely the case that if benzene is carcinogenic for mice, it will also be carcinogenic for humans. Okay, here's another one. So in a large majority of cases, so most of the time, if a patient has a sudden onset sore throat, pain when swallowing, a fever, red and swollen tonsils with white patches, then the patient has strep throat. So most of the time, if it's an A, then it's a B. Catherine has a sudden onset sore throat, pain when swallowing, a fever, red, swollen tonsils, white patches. Therefore, Catherine has strep throat. So this again follows this modus ponens, inductively valid modus ponens-like format. And this is actually the way that doctors reason They say, well, look, 95% of the time, these symptoms are associated with this disease. Therefore, it's most likely you have this disease. Now, in the back of their head, they know, 0.001% of the time, these symptoms are also related with African sleeping sickness. I'm just making this up. The doctor will not give you a prescription for African sleeping sickness because it is so rare. The first thing the doctor will treat is the most likely illness associated with the symptoms, which would be strep throat. Then if that doesn't work, you go down the list. So this doctors use this sort of reasoning. Yeah, okay. So what about this argument? Is this inductively valid? So most students at the Mississippi University for Women are women. Scarlett Johansson is a woman. So Scarlett Johansson is a student at the Mississippi University for Women. Is this inductively valid or inductively invalid? So look at the form. Most A's, students at the Mississippi University for Women, most A's are B's. X is a B, therefore X is an A. So that actually, this is the format, most A's are B's, X is a B, therefore X is an A. That is an invalid form. Modus ponens says X is an A, therefore, oops, X is an A, therefore X is a B. This is inductively invalid. Yeah. Okay, so that's an invalid argument. It gets this this backwards. It's what it commits the fallacy of affirming the consequent. Okay, here's another example. Someone who is a Sagittarius is more likely than other people to be generous. Marion is a Sagittarius. Therefore, Marion is more likely than other people to be generous. And there's the astrological forecast, I guess, of a Sagittarius. So this is an inductively valid argument, but it has false premises. I will contend that it's false, that people who are Sagittariuses are not more likely than other people to be generous. So even though it's inductively valid, it is not reasonable because it has false or unreasonable premises, unlikely premises. So it's inductively valid but unreasonable. We'll talk about astrology when we talk about confirmation bias more. Okay. So probabilities can be put in terms of percentages from 0 to 100% or from 0 to 1. This tilde is the probability of something not happening. So the probability of A plus the probability of not A is always going to equal 1. So the probability of something happening plus the probability of that something not happening is always 1 because they cancel each other out. And as the probability of A goes up, the probability of not A goes down. So there's this inverse relationship between the probability of A and not A. So you might hopefully have not had this experience where you go in, you get tested for some sort of disease, and as the test results come in, suppose the disease, whatever disease it is, you need to have, 10 tests before it's confirmed that you have this disease. As these tests come back positive, come back positive, come back positive, the probability of you having a disease goes up, while the probability of you not having that disease goes down. Okay, so reasonable or not reasonable? Okay, so is this a reasonable or not reasonable argument? 75% of dogs in the pound have had the rabies shot. Roscoe is a dog in the pound. Therefore, Roscoe has had his rabies shot. So first of all, is this valid or invalid? And then, is it reasonable? So it's reasonable, it's valid, and it's reasonable. So the argument form is valid. And each of these premises, if they were true, would render the conclusion reasonable or likely to be true. Roscoe has a 75% chance of having had his rabies shot if he is a dog in the pound. What about this one? 75% of dogs in the pound have had their rabies shots. Wally has had his rabies shot. Therefore, Wally is a dog in the pound. So this argument is invalid, and it's not reasonable. It's not reasonable because it's invalid. So in this one, this commits the fallacy of affirming the consequent again. 75% of dogs in the pound have had their rabies shot. Wally has had his rabies shot. This is saying 75% of A's or B's. X is a B, therefore X is an A. It gets it backwards again. Just because your dog has had the rabies shot, and I'm sure if you have a dog, it has had its rabies shot, does not mean it's also a dog in the pound. There are way more dogs in the world that have had rabies shots than dogs in the pound. So this is clearly an unreasonable argument because it's invalid. Okay, so let's take a stretch break here for a minute, and we're going to incorporate statistics into our inductive arguments. So go get a drink of water, put pause, and you can come back. Okay, check the time. 3:30. Make sure my watch is right. Yes, it is 3:30. Okay, so statistical argument. So in a statistical argument, it'll say that X% of a property is present in a population. So it'll usually be expressed this way. So X%, whatever percent of a certain property present in the stated population. So here's some examples. 18% of Americans smoke. 40% of the people in France are overweight. I'm not sure when these statistics are from, but it's surprising that more people in France are overweight than Americans. 35% of Americans are overweight. 1.4% of children who have are children who have autism spectrum disorder. So this is all 18% of the property. 18% of the property smokers are present in the population, Americans. 40% of the property being overweight is present in the population, French people. 35% property being overweight, population, Americans. 1.4% of the property, autism spectrum disorder in children. It doesn't specify children in the United States, it's just children everywhere. So we're going to talk about these things: measured property, target property, sample population, and target population. So let's talk about the difference between sample and target population. So because it's unrealistic, most of the time it's unrealistic to measure or to examine every single member of the target population, you select a subpopulation, a sample population. So a sample population is a subset of the target population. So suppose you want to know how many French people are overweight. You can't go around to every single French person and weigh them. So you take a subset of the French population and weigh them. That's a sample population. So the sample population must be representative. And this is really common sense. If you are trying to figure out what percentage of French people are overweight, you don't go and do your surveys at the gym because you'll get a skewed sample, or you don't do it in urban Paris. If you want to know what percentage of all French people are overweight, you'd have to make sure your sample is representative. So representativeness, the sample population must represent or resemble the target population in ways that are relevant to the property being measured. So a large randomized sample of people from different areas of the country with different ethnic, cultural, and economic profiles that matches the whole country. So if you want to know how much time Americans are spending on Facebook, and you just did your sample in rural Indiana, and you have, here I have an Amish family, you're going to not get an accurate statistic on the amount of time Americans are spending on Facebook if you just survey Amish people. For those of you that don't know, Amish people, or a lot of Amish people, don't use high-tech gadgets. So you want to make sure that your sample is representative in the ways that matter. Okay. So so here we're going to talk about, there's a target property and the target property and the measured property. Okay, so here's your target population, 300 million Americans. Here's your sample population, about 3,500 people. That's about the number that Gallup polls take for when they're generalizing about all Americans. So there's a difference between the target property and the measured property. The target property is what we're trying to get at. So suppose we're trying to figure out what percentage of Americans are obese. The target population is Americans, the target property is obeseness. The measured property is how we figure out the actual thing we're trying to get at, which is obeseness. So a measured property could be, it's just the way that we figure that out or measure it. So the measured property could be just grabbing people off the street of New York and weighing them. It could be giving people a dunk test to measure body fat. That's when you submerge someone in a tank of water. Or you could just do a phone survey and ask people over the phone if they're overweight. You could have people check off a box. So the measured property is the way that you measure what you're actually getting at. Okay, so a lot of times surveys go wrong because the measurements differ from the target property. So you can imagine if you call people up on the phone and ask them, hey, are you overweight? They'll probably say no. They'll probably say no. So you're trying to get at the percentage of people that are actually overweight. If you measure it by asking them over the phone, you probably won't get an accurate representation. So here's the difference between measured properties and target properties. So suppose you want to figure out how many bikes are stolen on campus, and the way you measure it is you look at people who have reported bike theft to the police. So here you can see a problem already. The measured property is going to undervalue. So people who report their bikes stolen are a lot less than people who have their bikes actually stolen. So this is not, the measured property is going to be undervalue what's actually the case. How about this? Reported rape or sexual assault. That's the measured property. What you're really trying to find out is how many students or how many people in the city were raped or sexually assaulted. And again, the measured property is going to be off. You're not going to get an accurate measure of your target property if you just look at reported rapes and sexual assaults, because statistically only 1 in 4 sexual assaults are reported. What if you're trying to figure out how many people have affairs? And the way you do that is people who report having affairs on a questionnaire. It may, probably a lot of people won't even admit it if it's even if it's on a confidential questionnaire. Target property voted for Hillary, reported that they would vote for Hillary. This is on here because last semester I gave this lecture the day after the election, and we were talking about why the polls were off, and so perhaps people were reporting that they would vote for Hillary when they actually obviously did not go out and vote for Hillary. So the poll said that Hillary was way ahead, where she definitely was not. People discovered 24 hours later. Here's another one. You believe that life evolved on Earth. is different than actually believing that life evolved on Earth. Is different from checking a box that says that you believe that life is on Earth. Again, here's a measured property, testing positive for Ebola, having Ebola. This would be more accurate, the measured property to the target property. And then finally, reporting that you have a STD obviously is going to be different than actually having one. So it's important to look at how the surveys are taken, how the questions are taken, to see if the statistics really are accurate. So in order for a statistical argument to be strong, to be reliable, the measured property should be an accurate indicator of the target property. So if you ask, suppose that you tried to, I don't know, figure out what percentage of UNLV students had STDs by going into an auditorium and asking people to raise their hand if they had an STD. That would not be, obviously, the measurement, the target, that's the measured property is not going to be even close to the target property. People will not raise their hands. A better way would be to fill out an anonymous questionnaire. So the way that you measure something is really important. So again, another thing to be aware of is a margin of error. The margin of error is the extent to which researchers believe the presence of the target property in the target population may vary from the presence of the measured property in the sample population. So it's very typical, a 3% margin of error. That's the margin of error in Gallup polls. So for example, if your statistics say that 18% of the sample population smoke, it could be that anywhere from 18 minus 3 to 18 plus 3, 15 to 21% of the target population has the target property. 15 to 21% of Americans smoke. Okay, so let's review some of these definitions. The sample population is the group of objects that the study actually measures. The target population, the largest group of objects that the study seeks to draw a conclusion about. The measured property, the property or feature in the sample population that is actually measured in the study in question. The target property is the property or feature in the target population that is central to the overall argument. So it's actually what you're trying to get at. The percentage of smokers smoking in the target population. Okay, so here's an example of a statistical survey on surviving lung cancer. Here, in a broad survey of the medical records of more than 10,000 cancer patients across the country, researchers at Johns Hopkins have concluded that 82% of stage 0 lung cancer patients whose cancer is detected early survive. Over the course of several years, the records of 10,452 patients were carefully reviewed to determine at what stage the cancer was detected, how it was treated, and what the survival rates were. Early detection was defined as cancer that was confined to a small area of one lung. Survival was defined to mean surviving 5 or more years after diagnosis. So here's the study, the survey. Okay, here's the conclusion. 82% of people with stage 0 lung cancer survive. The sample population was 10,452 patients at Johns Hopkins. The measured property was the medical files. That's the way they measured the survival. The target population is all people who have lung cancer that is detected early, and the target property is survival of 5 or more years. Now suppose that, okay, so here's a graphic representation of this. So here's the target population. 82% of lung cancer victims survive. So we want to generalize this to the population. Look, if you have early stage lung cancer, it's detected early, then you'll survive. Here's the sample population. So compare the statistical approach with the anecdotal approach. So suppose you get diagnosed with early stage lung cancer, and you tell someone at work, and they say, "Oh man, I know someone who had early stage lung cancer and they died." That's going to make you feel as if you don't really have much of a chance. But and it'll make it seem like that for that person if you know someone who's had early stage lung cancer and that they died. But look, here, if you look at the statistical study, the statistical argument, really it shows that you have a very good chance of surviving if you detect your lung cancer early. So here, look, here's the structure of statistical argument. In a group of 75,000 people, 21% of them smoke one cigarette a day. Oftentimes, the conclusion will just, they'll skip premises 2 and 3 and just say, therefore, 21% of all Americans smoke one cigarette a day. But it's important, if you looked at a more detailed account of the survey, they'll fill in these other premises. So premise 2, the composition of the group is representative of the target population, and 3, the measured property is an accurate measure of the target property. So they'll try to defend that the way they measured a person's, how much people smoke, actually reflected how much they did smoke. So asking how much you smoke is the same as how much you do smoke. Okay, so here's our summary of 8 concepts. Sample population, the group or object that the study actually measures. Target population, the largest or larger group of objects that the study seeks to draw a conclusion about. The measured property, the property or feature in the sample population that is actually measured in the study in question. The target property, the property or feature in the target population that is central to the overall argument. The accuracy, the measured property must accurately indicate the target property. Representativeness, the sample population must represent or resemble the target population with regard to other properties that are connected to the property in question. And then the margin of error, the extent to which the target population varies from the presence of the margin property in the sample population. And then random sampling. If a sample population is randomly sampled from the target population, that means that every member of the target population had an equal chance of being chosen for